Hello students, good evening to all. In previous class we discussed about calculation of electric field intensity due to an electric dipole at axial and equatorial position. Okay. So in this class we discuss about an interesting thing, that is electric lines of force, electric flux, ideal dipole, Gauss law and its various applications. Okay. So when you consider a charge, then you find a charge has a certain region, okay, and that region is called electric field. Okay. But when we look forward the region, we find always a charge experience some lines of force in order to represent its electric field. Okay. So that's why these lines of force are called electric lines of forces. Okay. So generally when you consider a isolated charge or single charge or the combination of charges, in each cases we find the electric lines of force. Okay. But it is easy to represent the electric lines of force by considering two different charges. Okay. Suppose the electric lines of force, if we move towards the definition, okay, so electric lines of force are the imaginary curves. Okay, that means we cannot see the electric lines in the naked eye. Okay, the electric lines of force always taken as imaginary. Okay, and they always starts from positive charge and ends at the negative charge. Okay, and when you consider two different charges close to each other, then in such case the electric lines of forces are curved lines. Okay, so that's why a simple definition of electric lines of force we can draw, that is electric lines of force are the imaginary curves which are drawn in an electric field such that tangent at any point gives the direction of electric field intensity at that point. Okay. So if you consider by taking such an example, like suppose this one is a positive and this one is a negative charge. Okay, if I consider the lines of force, then in case of plus and minus, the electric lines of force always starts from the positive and ends at the negative. So that's why my arrow sign is from positive charge to negative charge. Okay, here also this one. Okay, electric lines of force, you can do more electric lines of force like this. Okay, they only starts from positive, ends at the negative charges. Okay, and these are generally curved lines. When you consider two charges close to each other, they represent curved lines. Okay, and when we take any point on that lines, okay, if we consider a point on that line and draw a tangent at that point, okay, if I draw a tangent on that curve, then the tangent will represent the direction of electric field intensity. Okay, the tangent will represent the direction of electric field intensity at that point. Okay, if I consider here a point and draw a tangent, then the direction of tangent will represent the direction of electric field intensity or the resultant field. Okay, so at a single point there is a single tangent. Okay, and the direction of tangent is the direction of electric field intensity. That's why we write the definition like the electric lines of force are the imaginary curves which are so drawn in electric field such that tangent at any point on that curve gives the direction of electric field intensity at that point. Okay, and if we consider electric lines of force, then oftenly electric lines of force always starts from the positive, ends at the negative charges. Okay, so let us discuss what are the various properties that electric lines of force possess. Okay. So, properties of electric lines of force. Properties of electric lines of force. So, first property, electric lines of force starts from positive charge and ends at negative charge. Okay. Second thing, that is, if we draw a tangent at any point on the curve gives the direction of electric field intensity. Electric field intensity at that point. So, tangent at any point gives the direction of electric field intensity at that point. Number 3, that is, if we take uniform electric field, in case of uniform electric field, the electric lines of force are straight and parallel. Okay. So, this will represent a uniform electric field. Okay. So, in an uniform electric field, the electric lines of forces are straight and parallel. Okay. And in case of non-uniform electric field, the electric lines of forces randomly oriented. Okay. So, that will represent non-uniform electric field. Non-uniform electric field. Okay. So, in a non-uniform electric field, the electric lines of forces are randomly oriented. Okay. What is the fourth property? The fourth property in electric lines of force, that to measure weak and strong field by considering the electric lines. Okay. Number fourth property, we can say the electric lines of force when closely packed. Okay. When electric lines of force, that means the spacing between the electric lines is very small, then they represent a strong field. Okay. So, the electric lines of force which are closely packed, okay, or the line spacing between the lines is very small, then we can show that is a very strong field. Okay. And when the electric lines of force are loosely packed, that means the gap between the lines is very large, they represent a weak field. Okay. So, in any weak field, the electric lines of force most oftenly loosely packed. Okay. Number 5 property, that is most important property on electric lines of force. Okay. That is, two electric lines of forces never intersect to each other. Never intersect to each other. Okay. Two electric lines of forces never intersect to each other. Okay. Why they never intersect to each other? What is the reason behind that the two electric lines of force never intersect to each other? Two electric lines of force, we say, never intersect to each other, and this is the reason why they never intersect. Suppose this one is my one electric lines, okay, and this one is my second electric lines. Okay. So, if two electric lines of force or intersect each other, then what happens? We say in the definition, if we draw a tangent at a point, then the tangent will represent the direction of electric field intensity at that point. Okay. And at a single point, we can represent a single electric field intensity. Okay. So, if we intersect two electric lines of force, what happens? At a single point on the curve, there are two different tangential directions. Okay. There are two different tangential directions at the common point. Okay. So, for the two different curve, there will be two tangential directions. Okay, that means there will be two direction of electric field intensity, which is not possible. Okay, we say on the curve at a single point there is only one direction of electric field intensity, but here there will be two tangential direction of electric field intensity at a common point. So that's why two electric lines of forces never intersect to each other. Okay, so never intersect to each other. If they intersect, then at the point of intersection, there will be two tangential direction of electric field intensity, which is not possible. Okay, so that's why two electric lines of force never intersect to each other. Okay, number 6th property. Number 6 is also an interesting property, that is, the electric lines of force never pass through the conductor. Electric lines of forces never pass through a conductor. Electric lines of force never pass through a conductor. That's why electric field inside the conductor is 0. Okay, inside the conductor the electric field intensity is always 0. Okay, number 7 property that we can say, always a single isolated charge, okay, a number of lines of force associated with a single isolated charge is always 4 pi. So 4 pi lines of forces associated with a point charge. 4 pi lines of force associated with a point charge. Number 8, okay, if I consider isolated positive charge or isolated negative charge, in case of isolated charge the electric lines of force are straight. Okay, and if I consider isolated positive charge, then the electric lines of force ends at the infinity. Okay, for isolated positive charge the electric lines of force ends at infinity, and if I consider isolated negative charge, then the electric lines of force starts from infinity. Okay, if I consider isolated charges, then for isolated negative charge the electric lines of force starts from the infinity. Okay, if I consider two similar type of charges close to each other, either plus plus or minus minus, in such case the electric lines of force repel to each other. Okay, if I consider two similar type of charges, then the electric lines of force always repulsive nature. Okay, so electric lines of force for similar type of charges is always repulsive nature. For isolated charge, isolated positive, they ends at the infinity. For isolated negative, they starts from the infinity. Okay, so these are the properties that electric lines of force possess. Okay, and an important thing is on electric dipole is that what is an ideal electric dipole? We know what is an dipole. Okay, electric dipole means two equal and opposite charges separated by some distance will constitute electric dipole. But what is an ideal electric dipole? What is an ideal dipole? What is an ideal dipole? So ideal dipole is also an electric dipole that can be defined as like an ideal dipole consists of two equal and opposite charges separated by very small distance, separated by very small distance. That's why the size of an ideal dipole is 0. Okay, so size of an ideal dipole is approximately 0, but it has a permanent dipole moment. It has a permanent dipole moment. Okay, so we can say in case of ideal dipole we may approach 2a tends to 0. Okay, so an ideal electric dipole consists of two equal and opposite charges separated by very small distance, and the small distance may be tends to 0. So that's why we say size of the electric dipole is nearly equal to 0, but it possesses a definite or permanent electric dipole moment. Understand? So I think all of you get some idea what electric lines of force says and what is ideal electric dipole. Okay, so next we discuss electric flux and Gauss law with its various applications. Thank you.